And as soon as I got that rolling, I will drop a link for everybody into the chat. That should be live. Let's do that again. Go again. There we go. I will. All right, there we go. Linkage. We are going to wrap up module 10 about I/O. It's kind of part 2, but it's more like part the last quarter, the last 20% or something. Okay, we've hit all the concepts. We just want to do a little bit of implementation in LC3. Okay, so I'm going to rock and roll. I'm going to go. It's 11:30, and I have decided to rock my Hawaiian shirt. It just feels, you know, it's the downhill stretch, man. It's just, you know, it's just the downhill week, baby. And what happens after that is a little summer action. And I already decided I'm going to go to Hawaii in January. There's a conference that I'm going to attend. And on Thursday, I will reach max immunity and become immortal on Thursday, post vaccination. So I'm kind of feeling my oats right now, and it just seemed like the I could try to dig out the puka shells, but I decided to just roll with the Hawaiian shirt for now. Just so you understand what's going on, okay? Because there's a time to celebrate, and it might be a premature celebration penalty. That is possible, but I'm willing to take a chance on it. So, okay, are we ready? The last thing we talked we talked about the whole synchronous asynchronous. Hope you got that. I think you did. And what I want to do now is talk. There's just a little bit more concept, and then we're into details in the LC3, and then I'm going to jump over and do some details in the LC3 about this. Well, what I'll do is actually I'll talk a little bit about the trap instructions, and I'll try to jump on the LC3, the simulator, and then you know uh, show you a little bit more, of what's going on there when we get into the grunge, and then it's critical that you have to do that grungy thing yourself. Okay, you have to go get your hands dirty in that in the simulator. You have to get this. Okay, you can't just watch it and then know it. It's not going to work. All right. All right. So we talked about doing this communication, asynchronous versus synchronous. And what we're rolling with right now is this notion. These are terms, by the way. Protocol is a term, and handshaking is a term. In computer science, in data communications and networking. All right. Um, in real life, we have these things. Well, we have handshakes. We used to, right? Uh, right. I mean, we used to do. I think I don't know. What do we do? The handshake has gone the way. Are we going to go back to it? You think? Are we going to maybe just be fist bumping forever? I don't know. I think personally, and I was having this conversation with one of my sons who served a mission in Korea, and we both agreed that if we could do the bow, if we could adopt the Asian bow, that would be sweet on a lot of levels. So that's my what I'm advocating, that we just go to the bow, the respectful bow. So much about it that's fantastic. And the handshake is a little bit aggressive. It's a little bit like, I don't know, sweaty palms, whatever. The fist bump is a little, I don't know. I don't think we have a good outcome here. Or just the no look. There's the high five, the low five, and the no five, where whatever. There's just no greeting. So I don't know what we're doing. But the point just being that we have protocols, right? That's a word in English that just refers to it would be interesting. Would somebody mind like just dragging up a dictionary definition of protocol? Just I don't care what dictionary, maybe even the first thing Google serves you up or whatever. Doesn't much matter. I just want to see. Would one of you guys be willing to do that? Just drop that in the chat. Um, Because in the concept of protocol, we use it to talk about like let me see, what do we got? Gomez, the official procedure or system of rules governing affairs of state or diplomatic occasions. Sure. It doesn't have to be that, official, right? It doesn't have to be that formal, right, for it to make sense. What else we got? Matt, a set of rules governing the exchange or transmission of data between devices. Wham, wham, wham. I don't want devices yet. Let's go, Matt, on that same spot. Do you have like it not computing? Like what does one, two, or three say, Matt? If you wouldn't mind dropping those. It's great. I mean, we are talking about, it is a computer science course, but what do we got? Definition, an original, let me see. So we'll ignore number one, Texas. Thank you. We'll ignore number one, ignore number two with the memorandum. Okay, 3A goes a code prescribing strict adherence to correct etiquette and precedence, as in diplomatic exchange or military service. Um, yeah, and then it goes 3B is about networking data communications, right? Right, and there's also 4A there on Texas is, a detailed plan of a scientific or medical experiment, treatment, or, we articulate. But the bottom line is that when we say what's the proper protocol, right? If you're going to go in and, whatever, if you're going to go meet the Queen of England or something, I have seen the Queen of England, but I've never met the Queen of England. Um, but there's a thing you do when you enter the room, that this is protocol. But we have less formal things when you meet somebody, right? When you meet somebody for the first time, right? Traditionally, again, pre-COVID, I don't know in other words, the protocols are been thrown into disarray, I think. But back then, right, you'd just be like, "Hey, Biff, this is my friend Bob," and Biff would say, "Hey, Bob," and then would give the handshake, and then there's all these dynamics about what handshakes mean. It's all part of the protocol, right? There are some circumstances, um, I don't know if you ever watch the Hollywood self-congratulatory events like the Oscars or whatever. There's always this thing where there's like different rules for men and women, and like who gets the kiss on the face and who doesn't, and right. But that's really all kind of, you know, built into the protocol, And I remember, I've had situations where, I'm in Europe or whatever, and greeting friends, and first time I had a woman kiss me on the cheek, that wasn't my wife. I mean, on the way in, I'm like, whoa, what's going on? I don't understand the protocol. Is the bottom line. Then, of course, you realize it's very tender and it's a very cool thing, but you've got to get yourself in, to understand what the protocol is. So, you know what I mean? But it's all about, and then we have these informal protocols, really informal, right? Where when you're talking to somebody and you're going, "Hey, what's up?" Right? Now, if you walk into a situation, two people approach each other, and one of them is silent and the other one just goes, "On assignment 12, question 4, blah, blah, blah," you would find it a little awkward, right? It would feel maybe a little too abrupt. Like, what are you doing? With like, or then maybe you'd fear like, not fear, but what I mean, maybe suspect that is this person maybe a little autistic or a little struggling social skills or so, because it's like they're ignoring a normal protocol. Here's how it goes, right? You approach somebody and you say, you're like, "Hey, you do this thing. Hey, you make eye contact, and then they return it. You go, "Hey," and they go, "Hey," and then you can tell by their body language whether they're going to approach you or ignore you, right? They can go, "Hey," and then they avert their eyes, pivot their body language slightly away, and you can tell they're going to walk past you, right, in the hall. Or you go, "Hey," and you can also go, "Hey," and that's kind of like acknowledging you. There's also like, "Hey," it's like, "Hey, it's been a long time since I've seen you," or "I just really like you a lot, and I'd love to." There are some that are invitations to stay and talk, and others that can. There's a lot of nonverbal communication on "Hey," right? You know this, right? You get this. This is built into your social structure by just growing up. And for anybody, and I'm speaking of kind of an American standard, right? Kind of, at least in my sort of growing up and living here. For everybody who's grown up either outside of America, or grown up, maybe here but with a different culture in the home, could also be parents from another country. But there's other dynamics, right? That other social dynamics that are at play, and there's also regional dynamics. You know what I'm trying to say? Well, all I'm really trying to get at is that there is this process that sometimes culminates in a handshake. And what are we doing? We're trying to negotiate our way into a point where we can exchange information. That's what we do. Now, when you take this to things like dating, holy crap, right? Then it's just like, huh, you know what I'm saying, right? Well, I texted her, and then we had a really great date, and then I texted her and said, hey, it was a really great date, and then she ghosted me, and then you're like, how long do you wait until you respond back and say, hey, is everything okay? Or now are you stalking? Or is there just a point where you're just like, you ping one more time in a week, and then if she ghosts you some more, then you're done, right? You know what I'm saying? These dynamics are at play. These are protocols. That's all those are, is protocol, and they are communication protocols. And when you get into data communications and you actually study data communications, it's all there, man. It's all there, baby. Everything you deal with, in dating, in personal relationships, in conversations, trusted relationships like intimate partner, you know, intermediate relationships, roommates or friends or business partners, more remote, right? Every single thing that you deal with when you are trying to manage the protocols of interpersonal communication exist in the protocols of data communications and networking, which is actually pretty freaking cool, in my opinion. Um, Junlin, the question you've been asking yourself for years, I'm dying to hear it. Wait, what is the question that you've been asking yourself for years? When is the ghosting tell you it's over? Right? Is that it? Um, right. So yeah, when to give up on a girl? Yeah, right. Um, so Texas is like, it's like trying to ping a server and the server doesn't respond, right? There's got to come some time, right, where you are just like, I have no acknowledgement, but I gotta cut this thing off, right? I can't, because if someone ghosts you, right, and you persist, now you're a creeper, and you don't want to be a creeper. Or maybe you do, but if you do, we got to talk. Or maybe you don't have to talk to me, but talk to somebody. You need some help. Don't be a creeper. Um, uh, let's see. All right, Trent. Maybe somebody can drop in there and talk about how do you check the rightmost bit in machine code. Great question. And that is off topic, so I'm not going to go there. Okay, Trent, for now, because I think that, and if anybody else has any like ideas for Trent, please jump in and help. Right, I really, really, really want you to to help each other. You know, and there's a couple of ways of doing that. Okay, if we have time, Trent, we can talk a little bit about it. Okay, so, but that's protocols. And there's got to be a method somehow. And when you get into the elaborate data communication things, like when you're trying to manage a Bluetooth connection or a Wi-Fi connection or Ethernet or whatever, then those rules get really, really kind of crazy in terms of, how you do what you do. Um, Not unlike personal communications. But when we start to talk about something like I/O, it's actually quite a bit more simple than that. Okay, it's simpler than interpersonal communication, really. There are fewer dynamics, fewer options, fewer moving parts. Okay, um, and also Trent, don't say Trent, don't say sorry. Seriously, it's a great question, and it's germane to the class. So, okay, Trent, don't say sorry, man. This is not the place for that. We are just here to help each other. Okay, so we got to have, some mechanism, right? And I already talked about all that. Ground rules, assumptions. How does this thing work? Okay. Now, here's the way this thing works. There is this thing called the ready bit, okay, that we're going to talk about. And this actually, weirdly enough, relates to what Trent said. The user types a character and the ready bit gets set, okay? Then when your program reads the character, the ready bit gets cleared, okay? Um, the problem is if there's resource contention where multiple programs are trying to access the same, keyboard. How do you manage that? That's the job of the operating system. Now, the LC3 simulator, there's no operating system running on that thing. You own the hardware, man. When you fire up the LC3, you own the hardware. And but in a real system, there's almost always an operating system, and in that operating system, there's going to be a keyboard driver, and then the operating system is going to decide who's got the focus on the keyboard, right? Because you know how that is in your app. You can uh, highlight different programs, and depending upon which one is currently highlighted, when you start typing, that's the program that's going to receive your keyboard input or your arrow keys or whatever, right? Um, when I come over to my slides over here on the big screen, I have to click once. Um, then I can use my arrow keys unless I switch back to Discord or my OBS streaming, whatever. I've got to manage the scope of sort of where the focus is. Okay. Anyway, there's a bunch of stuff you'll deal with in operating systems that deals with this idea of a semaphore, where you're essentially protecting multiple people. Because here's the problem. Here's the problem. Imagine that one program reads the ready bit and then stops for a second. And then the other program reads the character, which clears the ready bit. Now the character is not there. Next program goes back and reads, but there might be a new character. When you've got that interplay, you need to make sure that I'm checking for the character and then grabbing it as kind of like a cohesive idea. And that's really just kind of a pre-pointer to operating systems. You'll see that again, okay, in when you start to study OS stuff. Okay, and then here's what I want to talk uh, about interrupt driven versus polling. These are, again, I'm not going to go super deep on this, and this is again a concept that's going to show up in operating systems and in system level software. Okay, so it's a little bit of a teaser for stuff that's going to be coming. With polling, the idea is that I'm just going to check, like that ready bit we were talking about. I got to have my program just going, check the ready bit. Check it again, check it again, check it again. Oh, it's on. We got a character. Read the character. Then it clears the ready bit. Check the ready bit. Check the ready bit. Check it. Check. That's just polling. So that's kind of like the kids in the car going, "Are we there yet?" Right? Are we there yet? Are we there yet? It's sort of a. And then what do you normally do? You guys mostly don't have kids. Some of you do, but then what you do is you say, "I will tell you when we get there," because polling mode is kind of exhausting, right? Burns all these cycles, and interrupt driven just goes, "Don't worry about it." And then when the moment has happened, you'll get a message, and that will alert you. It'll wake you up, right? So anyway, I don't know. Just to me, I got to come up with a better example, but I always just think about, there's like this bad guy villain, right? And then his phone rings and he's like, and he never says, yeah, it's like, because he's too cool for that. He just answers the phone. And then the voice just goes, it's done, you know, and that's his interrupt, right? That's bad protocol because and then he like, just like click. It's cool, but it's bad data communications because he needs to say hello or something. There's that handshake. and then so you know who you're talking to, and then acknowledge that you received the message. Otherwise, you don't. If you're the sender, you don't actually know. You know that dealing with a villain like that, it's not going to end well. So we're not going to get deeply into this here, but I just want you to understand. Again, these are two terms: polling and interrupt mode, or interrupt driven, or interrupts. Uh, in the hardware, there are these things that are like literally something comes from the keyboard, and the line kind of like goes live and creates this signal that the low level hardware will cause, you know, the driver to come alive and handle it, you know, that kind of thing. Somebody's handling it. Now in the LC3, there's like this magic layer that you don't see that because I'm gonna show you. You're going to go in there and we're going to actually go inside the trap instruction that handles the keyboard, reading the keyboard. Okay. And you're going to see that ready bit, and then the character shows up. Um, anyway, underneath there's stuff going on conceptually that you don't see, but which would have to be there in the hardware for that to actually work. And that includes some interrupts and stuff, but it's hard to see it. Okay. So what I'm going to do is walk through. By the way, yeah, okay. So Trent, I just want to say as a quick note, I really, really like what June Lin just said. Now, there's another thing, man, I think that might even just be the very best. If you don't want any confusion, you mask everything else away and then you just check to see if it's non-zero. That's what I would do. You could also multiply it by 2 7 times and then check to see if it's negative. Eh, just keep moving that bit left, left, left till it, you know. Has anyone noticed that the LC3 doesn't actually handle overflow? Have you noticed that? I mean, conceptually it's there, but you know, anyway. All right, input from a keyboard. So here's the deal, and I'm going to show you these in the actual registers, but um, remember we talked about this, we have this keyboard data register. Don't worry about the acronym, okay? And then the rest of this, keyboard data register, self-explanatory. There's the data, there's the status. And Walter, we need to make a note to flip the order on these. I think we should talk about the status first because that's the thing you check first. So let's do that. Let's talk about, so right, there's a status and there's data. So there's a register for each one and they relate to the keyboard. So keyboard data register, keyboard status register. And what the keyboard status register does is it uses, this is exactly for the kind of a scenario that Trent was talking about. It uses the leftmost bit. Why? Quick guess? Quick guess, anybody? And all it does is say when there's a character ready, I flip that bit, I turn it on. As soon as the character has been read, taken away by a program, I clear it. It goes back to 0. Come on, anybody? You can use any bit for that. We're throwing away 15 bits here. Why use, right? We could use any of the 16 bits as the keyboard status register. Why do that one? Yeah, boom, Matt just said because it makes it negative. Yeah. Then all I have to do is just poll on, check that thing to see if it's negative. That's all I'm doing is just checking it over and over and over again. And when it's negative, I now can branch, right? I'm going to fall through. If it's not negative, I loop. And then when it stops being negative, I drop in. That's it. Make it simple. And then this one here, because the LC3 just handles basic ASCII, 8-bit ASCII, we only use half of the keyboard data register. The other half is just thrown away. We don't care. We're just not going to use it. If we were going to use double byte characters, then we would use both. But right now in the LC3, with this system, we just use the half, lower half. Okay. Again, that makes it easy to compare. That's it. So here's the deal. When you hit a key on the keyboard in the LC3, the ASCII code gets loaded into the data register in 0 through 7, and the status register bit is set to 1. In other words, that leftmost bit gets set to 1. After you read it, then we clear that status bit, and then whenever the next keystroke is read by the LC3, it puts it into the lower half of the data register. Okay, so here's the code. Now here's the thing. What I want to do is actually go here in the code. This code is in the LC3. Let's do that. I think that's better. Okay, and then I want to just show you this right here, which is the tricky part relating to memory mapped IO. What I've actually got here is when I get an address coming in, remember right there that there are these two locations in memory, FE00 and FE02. They are the magic memory maps, so that when you press a keystroke, LC3 puts the ASCII value into that location. Okay, and then sets the status bit in the other one. Yeah, I don't know why it skips FE01. I don't actually know, Matt. No clue. But those are the two spots in memory, FE00, FE02. So what you see here, we'll look at the code, but what happens here is when I ask to read the value at FE00, right? What happens is it puts that in the MAR. There's this address control logic that gets set here, and it talks to the memory or whatever, and so memory does whatever it can do. But there is no, you understand, there is no FE00 in memory, in the actual memory. Conceptually, yes. Actually, no. So when I give FE00 to the MAR, what happens is that logic causes this pass-through where you choose what's the input source that we're going to use. One option is to come from memory. The other option is to come from either the keyboard status register or the keyboard data register, right? So if I say FE00, FE00, then that was the status register, right? Yeah. If I do FE00, then this guy right there, KBSR, that is the line that's going to make it through the multiplexer, and everybody else will be blocked. That's the one. If I say FE02, then that's the one that's going to make its way through the multiplexer. And if I say something that's in regular memory, it's going to come out of memory. And this is just sort of open for other conceptual things that we don't care about right now. Then that's the value that gets put in the MDR, okay? But just understand that it's kind of a sleight of hand. It's a little bit of a magic trick. The notion that it looks like memory when you make the request, but this is looking behind the magician's, cape or whatever. This is what is actually there. These input device stuff or actual memory, and it's reading from not memory, it's reading from these keyboard things, okay? Let me show you this thing. And by the way, let me pull up the that graphic again, which was the interrupt services right there. I want to talk about this. That's just a horrible scan. What? Why is that so bad? Yes, I'm responsible, but I don't remember why that looks so bad. But this is an appendix in your book. Okay. Let me pull up. Okay. Oh yeah. blow it up just a little bit. No, that's probably okay. And again, can I remind you again? Yes, I can. I'm going to. You have to do this yourself. Okay? You have to. You're not going to get this by just, this is learning fluency of technology, language. Those have to be participation sports, okay? You can't just be a spectator and have it work. Here's what I want to do. I want to start because I'm going to tell you a little bit about the trap, the idea of a trap instruction. And I'm going to start over here by looking at the routines we care about. This one is called in. It is trap number 23. It's hex 23, by the way. Print a prompt on the screen, read a single character from the keyboard. The character is echoed into the console monitor, and its ASCII code is copied into R0. The high 8 bits of R0 are cleared. That's a lot. Let's look at get C, which is much simpler. Thank you, Matt. That works. Yeah, that's appreciate that. I know it's there. Also, I dropped a link in the chat one time, I think, as well. But get C, read a single character from the keyboard. That's all it does. That's the one we want to look at. Character is not echoed, which means it's not being printed out. But the ASCII code is copied into R0. Now, this part about copying crap into R0, you ever have like something on your glasses that you clean about 3,000 times, and for some reason it just doesn't, it's like still there. That's why I keep doing this. The protocol for LC3 with respect to the keyboard is that it's going to put it in R0. That's just the deal. Like, why is that? Why is that? Social contract is why. Okay. It's just, that's the social contract that we made with the LC3. That's it. Okay. Now, get C is what it's called, trap 20. Actually, let me go, I meant to go over here. So let's go to assemble, okay? And we're going to go .org 3000. That's going to start putting this in location 3000. All we're going to do is, that's all we're going to say is in, and then we're going to go .end. And then we could put a halt instruction, but I don't care for now. Boom. In. Now, if we look at the bit pattern, what is that? 1111 is the first 4 bits, right? What is that? That is the trap instruction. Okay. And then the bottom is 23. What is that? Well, that's hex 23, which we said was the in. I don't want the in, I want the get C. I'm a dum-dum. Let me back up. But it'll show us the contrast. So that's hex 23. So if we had simply said all ones, 0, and then 2, whatever makes 2, which would be 0010, and 3, 0011, that's this instruction. Okay, but let's do get C. Well, and we can actually, get C is 20, is 20. Check this out. Get C. Now this is still sitting over there saying in because we did the text, but let's change it here as well. Same thing. Okay, get C. And what we're going to do is we're just going to step into this thing. Now I want to show you, first of all, a cool trick. You see that 20 right there, hex 20? I'm going to jump to the very top. Okay, that's the top of memory. That's all zeros. All right. and there's values there. You're like, what are the values? These are actually all fallback. There's a single trap instruction for whenever you give an illegal trap instruction that's not supported. That's what this is. And then, but I'm going for 2-0. There it is. Now check it out. 2-0 goes 0-400. 2-1 says 430. 22 says 450. 23 is 4A0. 24 is that one. And then 25 is FD70. And then it goes back to the FD00 because none of those are supported. These are the addresses of those 6 routines. The routines are built into the hardware, okay? Let me see. All right, Walter just dropped a note for everybody. Okay, the way the trap instruction works, this is going to be teaser for the next lecture, which is trap routines. The way the trap instruction works is that if I back over, remember, if I go back to 3000, that's a trap instruction, okay? It's trap 20. And then I go back to, just go back to 0, and I can just scroll down again for effect. 40, 430, etc. These are the addresses. So when I call that trap instruction, the way trap works is it's almost like a call indirect. Remember how we did like a load indirect and a store indirect? This is call indirect. We call this a jump table. So when I say trap 20 for get C, what happens is the trap instruction, the LC3 goes, okay, trap instruction. Go look at what they call the vector table. Go look at the trap addresses. So it goes to location 20, finds that address, and then does a jump to subroutine to that location at 0400. Okay. So when we go back to the program where the program counter is, okay, which is 3000, there's get C just sitting there ready to go. When we step, now remember, I can do next, which fully executes the next instruction. I'll show you. We fully execute the next instruction, and you're like, what happened? Well, it's running the get C. Get C doesn't stop until you press key, okay? But do you see what happened when I press that key? Let me clear everything again. Just watch for a second, okay? I'm just gonna go, so next says if the next one is a subroutine, you run to the end of the subroutine, then you come back, okay? I say next, and everything kind of like, actually, I want to reset all the registers. Let's see. Okay, everything kind of goes what? So I notice I have no characters in my input buffer. I highlight the console and I press the letter K. And then it goes, oh, I'm happy, I'm on the next thing. I look up and those were all cleared, but now notice that 4B is the value in R0. What is 4B? ASCII table, anybody? Also, my ASCII table is clearly the most butt ugly ASCII table in the history of the world. Again, it's my fault. What are we looking for? Was it 4B? Yeah, up there, 4B. 4B. That's the uppercase K, which is what I pressed. Had my caps lock on. That was my problem. Okay? All right, that's when we just skipped over it. What we're going to do next is we're going to go step, which is going to take us in. Okay? Reset all the registers. Clear everything. I'm now going to step, which means If I call a subroutine, I go into the subroutine. If I call a trap instruction, I go into the trap instruction. Okay, I go step. Now, where am I? Remember from that table? Do you remember in the table that it said, in fact, let's go back there. Let's go back. That's 0400. Okay, when I was back here and we did 20 right there, it said 400 hex. That was the address. Now, well, and I can also, like the PC is at 400, I'm just going to jump to the PC. Wherever the PC is, I'm going to go there. That's the routine right here. That's the routine. Oh, one other thing I wanted to tell you was when you're here, you see all this right here. Once you get into the ones that are supported, it's going no op, branch Z, blah, blah, blah. You can ignore this because it's the LC3 simulator trying to tell you what that instruction means if it were an instruction. But you already know it's an address. So it's like, this is what it would be if it were an instruction. And you're like, shut up, I don't care. All right? That makes sense? You don't care. All right, so let's go back to X400. Again, I can also jump to the PC. But in this case, these are the instructions. So we do care about them. Okay. The first thing we're going to do, now notice an interesting thing, and this is going to teach you something about subroutines, okay, and trap instructions, which are a form of subroutine call. The first thing I do is I store R7 into a location 4008, which is just this spot here, which I don't care, right? What I'm going to do, if you look at it, this is again our kind of our engineering skills. I go, I'm going to store something, load something, branch, load again, load, and then ret. And ret is my instruction to return back from a jump to a subroutine. Okay, ret is short for return. I'm going to return back where I came from. Well, here's the trick. Are you ready? The way I go back where I came from is that on my way in, the system, when I call either a trap instruction or a JSR instruction or a JSRR, it takes the current in value of the program counter and just puts it into R7. Just uses R7 like a parameter pass, like a carrier. And notice that R7 has 3001 in it. Okay? Because we had just executed, we're in the middle of executing instruction 3000. What's the program counter? It's already been incremented. It's pointing at the next one. And then what we do, because we don't know if the code is going to trash R7, we store it away and just save it temporarily. So we start by storing R7 away into a spot. It's after the ret. This is code that never gets run. Okay, over here in 0408. And then notice, ignore the next 3 instructions. Then just before I return, I load that value from that location back into R7. Then I call the ret, and the ret takes the value in R7 and puts that in the program counter. Boom, teleported, I'm back. Okay, does that make sense? And I've got slides about that, which means those slides we can go a little faster because we're really talking about what's going on. So that's the first instruction, is just to save R7. And the last instruction before the ret is to restore R7. And then I return. So everything else is right here in these 3 instructions, okay, at 401 to 403, okay? Oh, no. Put on your investigative caps, and what do you see? You see at 406 and 407 2 values, FE00 and FE02. Does that ring any bells to anybody? that ring any bells, Bueller? Boom. FE00, FE02, right? This is FE00, FE02. Okay, it's the address. It's the address of the status register and the address of the data register. In other words, I've got to read the value in FE00 to check and see if there is something to read. Then I got to read the value in FE02 to read what's in the keyboard. Okay. Now here's another thing. Let's keep going here. I'm going to go, let's go look at FE00 and FE02. Okay, there's that keyboard in FE, right. Okay, notice that 4B is that last character that I typed in previously. But that's not the current character. But we don't care because the status bit is 0. It's like there's nothing there. Okay, now check this out. I'm just going to go over here and I'm just going to press a lowercase k that you can't see it, okay? But I just pressed a lowercase k. Now, what I don't know is the refresh cycle on this whole thing, because I think that if I like scroll off of it, maybe, I'm not sure when that gets actually refreshed. Okay. But I'm just going to do a step. Let's execute the next instruction where we store R7 into 408. By the way, you know what I'm going to do? Hang on. I'm going to do a quick trick because there's leftover stuff from the last time we ran this. Because I was like, why is there a value already there in 408? Because we ran this previously from 3000. That's what got put there. I'm going to clear the entire machine by literally just reloading the page. And we're going to go back here again, okay? There we go, get C. We're going to step into it. There we are inside the routine. Now notice at 408, there's nothing there. Everything's clean, everything's fresh. So the first thing I got to do is store R7 away, but R7 does have the return address. So I'm going to just store R7. Okay, look at 408. There, I just put it there. Now, and then when I'm done, I'm going to pull it from there. But here's where we do the cool magic. I load indirect from 406. Now that's, again, you got to have fluency with that instruction, which we talked about, LDI. I load indirect. So I go to 406, which is the address of the status register. Now this is a perfect example of why we sometimes need the load indirect, store indirect. I'm going to give you the address of where it is. You're going to use that as like a, double bounce to get to where the actual thing is. So FE00, okay, right. So I am going to load indirect from 406 on the status register. Now, by the way, let's go over there real quick. It's 0 and 0, okay? 0 and 0. Jump back to the program counter. So I'm going to go ahead and do the load indirect and put it into R0. Well, there, the status register says 0. Why? There's nothing in the input buffer. And then now I'm going to branch on 0 or positive. In other words, non-negative. I'm just branching just to the line above me. So it's like all I'm doing now is polling. This is polling, right? And I'm just going to go crazy now. Ready? Step, 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 step. I'm just clicking step over and over and over again, okay? I click step. It's polling because nothing has happened. Okay, now in the middle of the polling, I highlight the console, and I press the lowercase k. Out of just pure excitement, I want to know what is there. FE00, it's not showing yet. FE02, huh. Let me do the step. I do a load indirect. Now notice when I did the load indirect that time into register 0, that register 0 has 8,000 in it. And if I now go back, so it's more that question of like, when does the LC3 simulator put that in? If the simulator, and then you can see that it's there. If the simulator was true to what the hardware would do, as soon as I press the key, that number would be there. Okay, and what's over here in FE02? 6B, which is the ASCII character for the lowercase k. I'm going to jump back to the program counter. All right, I now have that bit, that number is negative. So I branch on ZP. I don't take the branch because it's not Z or P, it's N. Now what do? I load indirect from 407. 407 holds what address? FE02. I load indirect from it, which means I go get the value of what's in FE02, which happens to be 6B. So I lose the status bit in R0, but I now gain the character. That's it, done. Then I load from 408 where I stored away the return address. I put that back into R7, which we never used R7, so R7 happens to be okay still. It's good practice to go ahead and just to store and restore that R7. You'll see that a lot. And it's just because in case you trash anything, or if you call a subroutine inside of a subroutine, you know what I mean? Then stuff gets trashed. So it's just the proper standards. Okay, then we go step, and I notice I put it back, but it was already back. Then I call the ret, and what ret does, in fact, notice something interesting about ret. The ret instruction, if you break it down, okay, what is it? C1, C0? Get to my glasses. Yeah. C1, C0. I'm actually going to break this thing down, okay? C1, C0. Bit pattern, okay? What is C? A is 10, B is 11, C is 12, which means I've got an 8 and a 4, right? I'm running here on my new whiteboard, all right? That's 1, 1, 0, 0, then 0, 0, 0, 1, then 1, 1, 0, 0, and then 0, 0, 0, 0, okay? So that's C. Let me put an X in front of that, right? So that is the value of that ret instruction, okay? What I want you to do now is break it down. Go look at, and if you're like actively engaged, you got your own paper, you could be doing this and tagging along on this exercise, okay? But let's go over to, I don't think I grabbed the instruction set. Let me grab those real quick. The LC3 instruction set, as you recall, right here. Okay, let's look for 1100. There's the red instruction. Okay, now let's also, what else is 1100? Check it out. Check it out, friends. The ret instruction opcode is the same as the jump instruction opcode. You see that? It's the same. And what does jump do? It jumps through a base register. That's all it does. All the jump instruction does is says, I'm going to give you what's the register. And in that register is the address that you're supposed to load into the program counter. That's all jump ever does. What does ret do? It does that exact same thing. Where are we at? There. Except what? It just presumes register 7. That's all it does. It's just a jump with register 7 hard coded. That's ret. Okay. So we do it. We go step, and we're back at the instruction right after the get C. Okay. Now, some of you who either weren't here or haven't watched or weren't paying attention. By the way, are we still on is my audio still okay? I get this occasional, I heard a sound in my headphones. Okay, we're good. We're still good. All right. If you haven't been paying attention, you might ask, well, where's the character? Well, we didn't print it out, right? We only read it in. So it's in. It's right there. It's in R0 right there. Now at this point, I could do, check this out. At this point, let's do a trap instruction right here. F for the trap. And then I got to go back to where was the out, which is hex 21. So 0, 2, 1. That's the out. So let's just run that one now. I just dynamically just added an instruction in the memory, and I'm going to go next because I want to skip past it. Boom, there it is. Because it was just sitting there, you know. That's it. Okay. So what you see there is that's the code. That is literally the code for the get C instruction. Now let's do this thing again. I'm going to reset the registers, and I'm going to do next on get C, and I'm going to clear the output and clear the buffer. I'm going to go next on get C, and I'm going to go lowercase k again, okay? See, it skipped over. Now I'm going to go step into the out instruction, and there I am in 430. And at this point, it should be a little faster. Oops. I store R7 away because that's got my return address in it into 43B right there. That's where I'm going to put it. And I'm going to store I'm going to store R1 away into 43A right there, just storage space. Okay. What is that? What is 43A? Wait, do I want the out? Yeah. What is the 43A? Because I load indirect. Oh, no. I load. What I'm doing is I'm storing R1 because I'm about to trash it. And I want to put R1 back right there on its way back out. So I'm just saving R1 so I can restore it later because I'm about to trash it. So when I'm back, the registers will try to be the same. Okay, that's all I'm doing there. So I just save R7, save R1. When I'm done, I'm gonna restore R1 and restore R7. And then right here, man, these are the same 3 analogous instructions. Here we go. I'm gonna go. We'll go store R7 away, store R1 away. Now I'm going to load R1 indirect through 438, which is FE04. Any guesses? That's the status register for the output for the console. Okay. I'm going to check the status register. And what I'm going to see is that it's 0. Wait, no. That was the control codes. Yeah, it's not negative. It's not negative. Oh, and with writing, it's the exact opposite from reading. If it's one, I'm busy. Look it up when you're using it. But when you're writing, if it's one, I'm busy, and when it's zero, you're good to write backwards from the reading of the keyboard. All right, and then I take our zero, which is still our little lowercase k, and I store it indirect to 439. Location 439 has FE06, which is the output monitor data register. And as soon as I go next, boom, it shows up because I wrote it to a location and it showed up on the console. I restore R1. I put, get the value back, put R1 back to what it was, put R7 back to what it was, and then ret, and I'm back right afterwards. What do you think? It's a lot of detail, but I think the concepts should be starting to kind of converge. Like how do you work in this kind of space, right? So let me just do kind of a quick review then. So that's literally, we don't need to do this code. We've got the code in the LC3. So when we output to the monitor, there is they call it the display data register. I don't really call it, you can call it output, you can call it display, you can call it monitor, don't care. But they've got that half a word of the data register and then status register. When I write a value, then it sets it to 0, which says that the monitor is busy. So if it's 1, I'm ready to receive, and 0 says it's busy. When the monitor is done, it sets the status register to 1. So did I say that exactly backwards before? I might have. Let me start over. When the status register is 1, we're ready to receive. And then while it's busy doing its job very, very quickly, then it's 0 during that tiny window of time. That's it. That's the code we just walked through. And same idea, except now I'm putting something in the MAR in order to write. And where am I going to write? That address control logic. It's going to go, you know what? It's the data register for the display. That's where I'm writing. And then that's all tied into the hardware to like make the thing appear. And then all keyboard with echo is doing is you do the first one, then you do the second one, right? You poll and you read the keyboard and then you do the next one. That's it. That's it. And then we talked a little bit about, I don't want to talk too much about interrupt driven. I just want to say, we really already hit this. Let me see. Yeah, that's more than I want to say or get into. It's not on the module exams. Yeah, that's good. So what we've actually done there is not only finished the lecture on I/O, but kind of gave you the lecture on trap and on routines, which is kind of what's coming up next. And we've got 10 minutes right now, but the reality is we're going to get quite a ways through it because we've really already covered the bulk becomes review. And there's only 19 slides in this set. Okay. So let me just kind of go. Let me just dive in and because actually what happens after this in terms of lectures, this trap lecture, trap and subroutine lecture, is the next to the last lecture, and the last one is stack. And I promise you it takes less than a day to do the lecture on stack. So we're as far as covering the stuff, with Thursday and then next Tuesday, we're solid gold. I prefer to have a little room at the end, so we're not good that way, but anyway, this whole trickery where you put the addresses of certain routines in a trap table that's known to the system, that is normal, by the way. They will sometimes call it trap routines. Sometimes they'll call it interrupt routines. And they'll sometimes call it that table a vector table or an interrupt table or a trap table. It's a table of addresses, okay? And what I am not going to have a great opportunity to sort of show you and teach you, maybe we can do a help section in the mythical evenings if I'm ever available, which is how to do jump tables and actually build code using jump tables, right? So you could have like 20 states, right? And every state is a routine. The address of that routine is in the table. So when you're at state 0, you just jump indirect through location 0. When you're at state 7, you jump indirect through location 7. You see the trickery? Isn't that cool? And that then becomes the entire structure to drive your state machine. Crazy simple, as long as you can get all the addresses of all of your routines into that state table. It's the same idea, so it's teaching you the same concept. Okay? We talked about this already. We talked about the fact that we need to have some routines for some higher level of abstraction. That's all you really need to know from this slide. The trap routines give you this higher level of abstraction. And what really is happening here is like the user program's going, you get to this trap call, and that call goes joinky out here to this system routine that we just did. And then when it's done getting your keystroke or writing your value out to the display, then it returns back just to the next instruction. That's it. It's the same thing that subroutines do, okay? The very same things that subroutines do. Now, I want you to note one interesting thing. We talked about how the jump instruction and the ret instruction are the same instruction, right? Crazy but true. But notice that the trap instruction is 1111, but the jump to subroutine instructions are not the same because they're not the same. The trap instruction you're gonna give it an index into the trap table. When I say hex 25, I'm telling you it's hex 25, meaning index 25 into the trap table. And if anybody's wondering, getting devious about, can you build that final project and build a state table by loading values into the trap table and using trap instructions? The answer is yes, you can. You can build your program where the entire control instructions kind of system are just trap instructions. Welcome to do that. It's a little cumbersome because you got to get all those addresses into the trap table. You got to be writing those things to those locations, and that's kind of a pain. Whereas with our modified simulator, we have the ability to just use the labels from the symbol table. But just notice that they're different, okay? And there's also two different kinds of subroutines. One goes through a base register, the other one uses a PC offset, okay? All right, so we already talked about this, right? The set of service routines. And there can be up to 256 service routines. Why? Because we just decided, we being not me, decided that we were going to have a trap vector be 8 bits. That's it. That's what they decided. It was good that trap vectors were going to be 8 bits long. So they're going to be 256 of them. And then the system defined 6 of them for us by giving us their little number, 2021, which are just indexes into the trap table. You got this table of the starting addresses stored in these locations from 0000 to 00FF. We are already there. That's where we were. That's what I showed you. And then the trap vector is just the index into the table. And then you return just like you do from a subroutine. So these are the predefined trap service routines. And in the LC3 simulator, you can say trap hex 20, trap hex 24. You can say that, okay? You can also just say get C, put SP. You can use these. They function and look basically just like instructions, really. They look the same. How we doing on time? Oh, how are we doing on Dr. K fatigue? Not good. All right. So there's the trap instruction. Those are reserved. That's your vector. If you want to do a get C, you put 20 there. 0, 0, 1, 0, 0, 0. I'm talking technology. And then whatever these are, and if you want to define your own, you can put those there. That's it. And then this is the part I also showed you where basically, well, no, I didn't actually show you. Do I have a picture? Yeah. Okay. You take this trap vector, you sign extend it. Sorry. It's not signed. The trap vectors are not signed. They're unsigned. You zero extend it because it's unsigned. And then the entry at that location in memory, think about this. The trap table is at 0 location in memory. So trap vector 25, 25 refers to, it's like an index into the trap table. Well, what's the actual address in memory? 0025, because the vector table starts at 0. The entry at that location in memory is loaded into the MDR. I grab the PC and put it into R7, and then I take whatever is in the MDR, which would be that address, I load that into the program counter. That all should make perfect sense. And it's going to look like this. This one is doing vector 2-3. It sounds like you're being pretentious when you call it 2-3, but if you say 23, 23 hex is fine. 23 and getting confused with decimal, not fine. So there's the trap. That's 2-3. Goes to that location, grabs the address, and then, hang on a second. I don't have a cold. I swear. But it's kind of like an allergy thing. It gets a little scratchy. Ah. I can get through this slide if I can get my voice back. 4A0 is the address of the routine that runs trap instruction 2-3. So this is the process. Grab the vector, look it up in the vector table, pull the value out, okay, load that into the PC. You're now running code over here. And when you're done, you return back through the ret instruction. That's it. We talked about the ret instruction already, and I'm just going to let's end on this one. We'll come back with like 7 slides to go on this. And then literally the stack is next. So, but this just shows you the ret instruction and the jump instruction, where the ret hard codes the base register, but the jump doesn't. What if you do a jump with the base register 7? And the answer is, it's a ret. It's a little unusual in that respect. All right, we're out of time. This is where we're going to come back on subroutines. And this literally is like 7 slides. It will not be hard based on everything we've talked about. But that's all I got for today. And good luck with everything that's on your plate. I know it's a lot. How do I know? I was a college student, remember? For a long time. All right. See you Thursday.